My name is Peter Block, and I'm part of the Institute for Systems Research, along with my co-author and advisor, Dr. Sarah Bergbreiter from the University of Maryland. And today I'm going to be talking to you about large area, all, oh goodness, what happened here? It's going backwards? Oh, it's reversed, I'm sorry. I'll be talking to you about All-Elastomer Capacitive Tactile arrays. So robotics is a constantly advancing field, and we've continued to see more interactions with robots in our daily lives, with Roombas scooting along our floors, and demonstrations of personal assistant robots like Asimo eventually aiding the elderly. We must make certain that these robots are not only capable of sensing the world around them, but be able to manipulate and interact with it as well. Thus, by considering tactile sensation, we can help the robots know if a human hand or object is on a part of its body, or to be able to provide the tactile feedback to know the pressure needed to hold a glass of wine or a light bulb as seen in the shadow hand here. And also the change in grip needed for holding a 10-pound weight. Tactile sensors have been an area looked at for more than 30 years. Previous work includes a variety of flexible substrates, such as polymer foams, films, and elastomer channels, working with different properties like resistance, capacitance, or piezoelectricity to measure forces. Capacitance was chosen due to its high sensitivity and ability to provide high spatial resolution while sensing is independent of temperature change. Also, thanks to the ubiquity of capacitive devices in our lives, like our touchscreens on our cell phones, low-power capacitive sensing electronics are widely available. To match human touch, it's important that flexible materials are utilized to provide suitable conformation, as well as have equivalent range of forces capable of detecting. As seen below, the ranges and spatial resolution of the groups shown are great for matching the need for robotic fingertips, where such values are desired. However, when scaling these sensors up to larger areas, the conductive materials used can end up being quite costly and may not be as easy to manufacture for larger arrays. So while there are commercial sensors currently available for large-scale arrays, these too have sensors that end up being high in cost, with some being $10 per sensor or more. So what's needed is something that's very inexpensive to make while considering ease of fabrication, all while keeping the flexibility and sensor density needed to match human skin sensitivity along the arms, legs, and back. Thus, we looked at large area all-elastomer capacitor arrays. This utilizes existing off-the-shelf silicone sheets as a substrate, while a conductive polymer mixture of carbon black and PDMS is used to make the capacitors. Even at the laboratory scale, the production of these sensors was less than 5 cents per sensor. This fabrication can be done via roll-to-roll process, allowing for easy transition to industrial manufacturing, and likely capable of dropping the manufacturing costs to fractions of a cent. One sensor in this array is capable of detecting 0.5 millinewtons up to 2.5 newtons, this being akin to feeling the resting weight of a housefly all the way up to a large grapefruit on just one sensor. This large area design has a spatial resolution of 1 sensor per centimeter squared, but utilizing interpolation through programs such as MATLAB, sub-tactile resolution can be attained, as seen below here, where the approximate center point mass of 2 small Delring squares can be seen without directly being on top of the sensor. Now, looking at the theory behind this material, you can see that it can be modeled as a simple parallel plate capacitor. Thus, when a force or pressure is applied uniformly to the sensor compresses vertically and expands horizontally. The capacitance is a relationship between the sensor area, the dielectric thickness, and the relative permittivity of the material. And the calculation of change in capacitance includes Young's modulus of the material and the pressure applied, as well as a capacitive gauge factor. While alpha the capacitive gauge factor should be 1 for isotropic materials with a Poisson's ratio of 0.5, previous research has shown that this factor is less than 1 in experimental measurements. And a value of 0.5 was used by Wu et al. In their experimentation. Utilizing this equation, we should see a capacitance change of approximately 5.4 femtofarads per kilopascal. Fabrication of the capacitor array is quite simple and requires no cleanroom time. Starting with a purchased sheet of 10 mil 28 durometer silicone, cut down to a desired size, a 17.5% by weight of carbon black to PDMS mixture is combined together with hexane at a ratio of 1 to 4. The PDMS is at a ratio of 10 to 1 base to curing agent. This is then sprayed onto the sheet via powdered stencil, making a 3-second pass 3 times. This leaves approximately a 50 micrometer thick deposit of the conductive PDMS. The stencil is then removed and then cured in the oven for 1 hour at 125 degrees Celsius. To make the double-sided sheets, this pattern sheet is then flipped over and the stencil is applied and sprayed again, cured again for 1 hour, and finally vias are punched and filled with the conductive mixture and cured for the last time. For 2 layered sheets, the steps A through C are simply repeated on another sheet, and the 2 sheets are then stacked. So in order to profile the capacitive response of these arrays, a simple cantilever beam was used to place various forces on a given sensor. A small centimeter squared Delrin square was used to distribute the force over the whole sensor. For lower pressures, small 1x1 Delrin squares were stacked sequentially on top of the sensor. These changes in capacitance were measured via probes that were secured in place via styrofoam puncture. The probes were connected to an analog device 7746 evaluation board, and the sensing information was then collected and visualized in MATLAB as overviewed in this next slide, reflecting the current system, which utilizes an Arduino controller to communicate with the sensing chip as opposed to the evaluation board. Before discussing the results, a certain characteristic of these arrays must be highlighted. During the fabrication process, a slight bump is formed on the elastomer sheet. An exaggerated sensor profile of the bump is shown on the right. It's suspected that due to this bump, we see a very high sensitivity to the sensor. We've seen as on this next slide, pressures as low as 20 pascals were detected in this setup, and capacitance was way above expected theoretical capacitance. As seen on the exaggerated side profile, the mass of the small Delrin squares was not quite sufficient to flatten out the bump on the sensor. Extending this range to higher pressures, which utilized the cantilever beam setup, the bump was finally flattened out, resulting in a better linear response. However, this still didn't confer with expected theoretical results. But by tearing out the weight required to flatten the sensor, we were able to confirm that when finally flattened, the sensor responded well with the theoretical model. The stack sheets also showed high sensitivity at lower pressures, likely due to complex geometries that are not accounted for in our simple capacitor plate theory. However, when reading higher pressures, the slope matches well with theory. And while the bump may account for higher than expected sensitivities, with proper calibration, this can be utilized as a feature and aid in these sensors in determining a wide range of forces suitable for deployment in large-scale arrays. So the sensors outlined today are very easy to manufacture and not only are capable of immediate transition to mass manufacturing, but are also still highly sensitive, flexible, and incredibly inexpensive, making them suitable for large-scale robotic applications. Future work includes looking at further simplifying the fabrication process where a sheet is fully coated on one side with the conductive elastomer, thus removing the need for extensive vias. Work is also being done to test varying sheet modular thicknesses and spacing to improve the range of force detection and spatial resolution. Additional efforts are taking a look at hardware and onboard computing, while there are also pursuits in health monitoring where an elastomer bandage can provide information about heart rate, monitor breathing, and other aspects, as well as prosthetics prototyping, helping amputee victims obtain proper fittings with their artificial limbs, and providing feedback on how well they may be conforming, causing hot spots on the body. With that, I'd like to thank Dr. Bergbreiter in the Microrobotics Lab and acknowledge a grant from NASA. And thank you all for listening. I'll be happy to take any questions.